Okay, for our first problem, it states that oxygen gas can be produced by decomposing solid potassium chlorate, producing, there's our arrow sign, solid potassium chloride, and oxygen gas. Okay, so let's write this reaction. Potassium chlorate, okay, that comes from K plus and ClO3 minus. Okay, so that's K plus, and that's the polyatomic ion chlorate. Okay, so that's going to be KClO3, and it says that that's a solid, and it decomposes to produce potassium chloride. Chloride is Cl minus, KCl, and they said that that's a solid as well, and oxygen gas, which is a diatomic molecule. Next, we're going to balance these, so that's going to require 2 here, and 3. It's really the oxygens that make this evident. 6 oxygens here and then 6 oxygens there. So we're going to go through now, and we're going to do our BCA Stoich table. So I'm going to put B, C, A here. I'm going to make my dotted line right down the middle there, and one line here. I'm going to break this up. So before it said you have 138.6 grams of potassium chlorate. That's this. 130. Oh, I wouldn't put that there. On the side, I have to convert that to grams. KClO3 convert to moles, I mean. Okay. And it decomposes completely. So we start off with 0 moles of this and 0 moles of this. Let me convert that to moles. Real quick, we know that the molar mass of this is 1225.55 grams of KClO3. 3 Cl's, 3 O's, 1 Cl, 1 K per every 1 mole of KClO3. So we're going to do that, and when we do it out, I believe we get 1.131 moles. So that's going to go right here, 1.131 moles. And now that's our reference, because that's all we got. So 1.131 moles here. And we're going to add that to the product side in this case, 1.131 moles. That's going to be multiplied by the mole ratio, 2 to 2. Reference always on the bottom, 1.131 moles. Multiplied by the mole ratio there, 3 to 2. So all of the reactants used up, so we produce 0 moles there. Okay. This multiplied by 1 is 1.131 moles. But the question was asking you about oxygen gas. And when you do this out, you get 1.696 moles. And it asked for mass. So although this is our answer, we're going to go ahead and convert that to grams. So I'll do all my conversions over here on this side. 1.696 moles of O2. Per every 1 mole of O2, there's 32 grams of O2, and we're going to get 54.286 grams of O2. 54.28, because we have 4 significant figures here, and we have 4 significant figures there. So that's the answer for the first one. This problem, we're given a similar reaction. In this case, it's a decomposition reaction again, where we have the hydrolysis of water. So this is water splitting, liquid water splitting into its 2 atoms. So in this case, it's hydrogen gas and oxygen gas. We're going to balance this to 2. We're going to make our BCA table. BCA. Do all my conversions over here. So you have 60 grams of O2. So we're right here. Got to convert that to moles. 32 grams of O2. It's a good one to memorize. The molar mass of O2, that is. And I'm left with 1.875 moles of O2. It's going to go right into my BCA table. We don't mention hydrogen gas here, so we're just going to ignore that all the way through. And we have 0 moles of O2 at the very beginning. O2 is my reference, so we're going to work backwards here. Don't ever multiply the reference by anything. Plus 1.875 moles, but it's not that. That's O2. This is always 2 times that, multiplied by 2 over 1. And this is going to be 0 moles. Don't worry about that. And we're going to be left with 3.75 moles of H2O. And it's asking for grams of water. So I'm going to go over here to my conversion side. And 3.75 moles of H2O for every 1 mole of H2O. There's 18 grams of H2O. And I'm going to get 67.5 grams of H2O liquid. Okay. So 3 significant figures here, 3 significant figures here. I'm good to go. Problem. This is a limiting reactant problem, and it's definitely the more complicated one to balance. So what we have here is grams of aluminum sulfate reacting. That's what they want when solid aluminum, okay, so we have here Al solid, reacts with copper 2 sulfate. So copper in this case would be 2 plus because of that Roman numeral 2. Sulfates SO4 2 minus. Okay, so they balance each other out. Cu SO4 solid. Okay, and it says aluminum sulfate is what's produced, and solid copper. So let's do aluminum sulfate first. Okay, that polyatomic ion, in this case, you got to keep as one thing. Okay, you need 3 of those, just like as if that was one element. And it says solid copper is the other product. This is a pretty easy one to balance. Actually, you're going to put a 3 here, and then you're going to put a 3 here. So let's go through and do our BCA Stoich table. B, C, A. I'm going to do my conversions over here. So you have 23.33 grams of solid aluminum, okay, and you have 74.44 grams of solid copper 2 sulfate. So this is going to be a limiting reactant problem because you're given one of each of these. And remember, we need to convert these to moles. So over here on the side, that's what I'm going to do first. So I have 23.33 grams of Al. And I'm just going to divide that by the molar mass, 27 grams of Al per every 1 mole of Al. And when I do that out, I'm going to get 0.864 moles of Al. So 0.864 moles of Al. Okay. And then I'm going to do that for copper sulfate as well. So in this case, I have 74.44 grams of copper sulfate. And what I want to do is convert that to moles. So I have 159.6 grams per every 1 mole there. And I'm going to end up here with 0.466 moles. Okay. So you pick and choose. I'm going to choose this one first. And conceptually, when I look at this, I need 1.5 times as many moles of copper sulfate every time I have a mole of Al. In this recipe, I don't have enough ingredients. I have less copper sulfate in this case. So I'm going to choose this as my reference. I'm going to subtract out 0.466 moles here, and you'll see I'll end up with 0 moles here. That's the limiting reactant because it gets fully used up. And I'm going to subtract out 0.466 moles here, multiplied by the relationship between these two, which is 2 over 3. Okay. When I do that out, I get 0.553. Now notice, this problem just asks you for mass of aluminum sulfate produced. That's what we're looking for. But we've actually already solved for how much excess. Okay, we have 0.553 moles, and if we multiply that by 27, we'd have grams of aluminum excess. That's a big deal, okay, at least to me. Nothing's mentioned about copper. We're going to leave that alone. This started off at 0 moles. I'm going to add 0.466 moles of reference here, multiplied by, in this case, 1 over 3. And I'm going to add these up, and I should arrive with 0.155 moles of that. And the answer is calling for mass. So 0.155 moles of that per every 1 mole of that. The molar mass is 342.6 0.3 grams. That's coming from this, which is 2 ALs, 3 S's, and 12 O's. So you do that out, that's going to give you your answer, which is 53.23 grams Al2SO4 3 solid. Okay, now let's look at the difference between all three of these problems here. Okay. The first problem was a simple decomposition problem. There could not have been a limiting reactant because there's only one reactant. Notice we actually solved for both answers, but I asked for O2 as well. Advantage of the BCA table is it gives you all possible answers. Okay. Similar problem here, but we worked backwards. Now, since we're starting with reactants, it's going to get the minus, and the products are going to get the plus. And with the limiting reactant problem, you know you pick the right limiting reactant if you end up with 0 and a positive number of the excess reactants. Beauty of doing a BCA table this way is that we end up with not only the answer, but how much excess, which ends up being a really big deal.